Glucagon-like peptide 1 GLP-1 agonists, originally developed to improve blood sugar control in people with type 2 diabetes, have rapidly evolved into one of the most intriguing therapeutic tools in modern medicine. Initially recognized for their role in enhancing insulin secretion, slowing gastric emptying, and promoting weight loss, these drugs have more recently drawn attention for their neuroprotective properties. Mounting evidence suggests that GLP-1 agonists may not only regulate peripheral glucose metabolism but also influence sugar dynamics and glycogen turnover within the brain. This dual action offers a compelling therapeutic bridge between metabolic disorders like diabetes and neurodegenerative diseases such as Alzheimer's and Parkinson's. The brain, while often considered insulin independent, does in fact respond to metabolic hormones like insulin and GLP-1 in ways that are still being uncovered. GLP-1 receptors are expressed in various brain regions, including the hippocampus, hypothalamus, and cortex, where they appear to play roles in appetite regulation, neurogenesis, inflammation control, and mitochondrial function. When activated by GLP-1 agonists such as semaglutide or liraglutide, these receptors initiate signaling cascades that influence not only neuronal survival but also glucose uptake and possibly the regulation of glycogen metabolism in astrocytes. Astrocytes, the brain's key energy managers, store glycogen and shuttle glucose-derived metabolites to neurons. In situations of high energy demand, learning, stress, or recovery from injury, astrocytic glycogen becomes a critical buffer, maintaining synaptic transmission and protecting neurons from metabolic failure. However, in both diabetes and dementia, this system begins to falter. Insulin resistance in the brain leads to impaired glucose uptake, neuroinflammation, and dysfunctional glycogen handling, contributing to cognitive decline. GLP-1 agonists may help reverse or stabilize these effects. Preclinical studies show that GLP-1 agonists can cross the blood-brain barrier and reduce amyloid beta accumulation, inhibit tau phosphorylation, and improve synaptic plasticity, hallmarks of Alzheimer's pathology. Interestingly, these improvements coincide with enhanced glucose metabolism in brain regions affected early in dementia. Whether this is due to increased uptake, improved insulin signaling, or direct modulation of glycogen turnover remains under investigation, but the outcomes are promising. In mouse models, liraglutide treatment not only improved spatial learning but also appeared to normalize glucose transporter expression and astrocyte neuron metabolic coupling. A lesser-known but critical aspect of this story lies in the regulation of glycogen phosphorylase, the enzyme responsible for breaking down glycogen into glucose 1-phosphate. Some research suggests that GLP-1 signaling can affect the phosphorylation state of this enzyme, possibly enhancing glycogen breakdown under appropriate conditions. This would be particularly beneficial in the aging or diabetic brain, where impaired energy release from glycogen reserves may leave neurons vulnerable to stress, injury, or hypoglycemia. In Parkinson's disease, where mitochondrial dysfunction and energy deficits are key features, GLP-1 agonists have similarly shown neuroprotective potential. The mechanisms here may involve not just glucose homeostasis, but also antioxidant pathways, mitochondrial biogenesis, and inflammation suppression, all of which are closely tied to cellular energy status and glycogen dynamics. Brain regions like the substantia nigra, which are highly metabolically active, may benefit significantly from interventions that optimize energy substrate availability, including through glycogen mobilization. These findings help explain why GLP-1 drugs are now being trialed in Alzheimer's and Parkinson's patients, with early results showing slower cognitive decline and improved brain metabolism on PET scans. Importantly, this benefit may extend beyond those with coexisting diabetes. Even in non-diabetic individuals, GLP-1 analogs appear capable of resetting dysfunctional brain energy pathways, possibly by modulating glycogen storage and usage in key glial and neuronal populations. The implications of this are profound. If GLP-1 agonists can simultaneously regulate blood sugar, enhance brain energy flexibility, and reduce neurodegenerative burden, they could serve as a unifying treatment across metabolic and cognitive domains. This would be especially relevant in populations where type 2 diabetes and dementia often overlap, such as older adults with insulin resistance or metabolic syndrome. However, caution is warranted. The long-term effects of GLP-1 drugs on brain glycogen dynamics remain poorly understood. Overactivation of glycogen breakdown might, under some conditions, lead to energy instability or oxidative stress, particularly if not balanced by adequate glucose supply or mitochondrial capacity. Furthermore, these agents may interact with other hormonal axes, like cortisol or leptin, that also influence brain metabolism, adding complexity to their use. In summary, GLP-1 receptor agonists may do more than manage blood sugar. They could reshape how the brain stores, accesses, and protects its energy reserves. By modulating glycogen metabolism, enhancing insulin sensitivity, and reducing neuroinflammation, these drugs offer a rare opportunity to address two seemingly distinct epidemics, diabetes and dementia, with a single class of compounds. Continued research is needed to clarify optimal dosing, timing, and patient selection, but the potential for therapeutic synergy across brain and body is no longer theoretical. It is increasingly a clinical frontier.